Hi, I want to talk about the electric field that's created by a solenoid. Now, that sounds kind of weird because in chapter 30 we talked about solenoids as creating magnetic fields whenever a current passes through the solenoid. And that's true, but with Faraday's law for induction, as it relates to electrical circulation, changing magnetic fields can create electric fields. And anytime there is a changing magnetic field, you are going to create a circulating electric field around the region of changing magnetic flux. Now with the solenoid, if the solenoid is infinitely long, then we argued the magnetic field inside needs to be uniform. And the magnetic field in a solenoid would be equal to mu naught times the number of coils per length in the solenoid times the current passing through the solenoid. So if the current is steady, we have a flux, but the flux doesn't change. So we wouldn't have any electric field. But if the current is continuously changing, so let's say our current is sinusoidal with a function equal to a maximum current times the cosine of the angular frequency of oscillation omega times t. So, Faraday's law for electrical circulation says the electrical circulation, the integral of the electric field dotted with a path around some closed path, is equal to minus the change in magnetic flux through the cross-section that is created with that path as a boundary. So, to make things nice and simple, let's choose a circle where the center of our circular path is at the center of the solenoid. Well, that gives us two regions that we can look at. Outside the solenoid and inside the solenoid. And I'll take a look at outside the solenoid first. So the solenoid has some radius to it, let's call it capital R. And our loop for calculating or changing flux has a radius little r. So our circulation, our electric field, because of symmetry, should be the same all along the circular loop. So our circulation would just be the electric field times the circumference of our loop, 2 pi times our radius little r. Now for our change in magnetic flux, our magnetic flux would be our magnetic field dotted with the area, summed up over all of the area. Well, inside a solenoid, the magnetic field is uniform. So that flux would just be the magnetic field times the area where that magnetic field exists. And we said inside the solenoid it's everywhere, so that area would be pi times the radius of the solenoid squared. Outside, we said the magnetic field is practically zero. So our flux then would be pi times the radius of the solenoid big R squared times the magnetic field, which with the changing current would just be a constant mu naught times a constant n number of turns per length times the maximum current that we get times the only changing part, the cosine of omega t. So when I take the derivative of this, I have a whole bunch of constants, and the derivative of cosine omega t gives me minus omega times the sine of omega t. So that means I can clean up a lot. A minus sign there, and the minus sign I get from the derivative cancel out. I have pi on both sides of the equation, so pi cancels out. So in my numerator, I'm left with mu naught times the number of turns per length times the radius of my solenoid squared times my maximum current times omega sine omega t, all divided by 2 times our radius. So outside a solenoid, we create a changing electric field that falls off as 1 over our distance away from the very center of that solenoid. Inside, things are a little bit different. We would still get the same magnetic circulation term, 2 pi times the radius of our circle little r. But inside, our flux wouldn't be the whole area of the solenoid. It would just be the area of our loop, which would be pi times little r squared. Again, we'd have a pi on both sides, but now we'd have the same r on both sides, which means the 1 in the denominator cancels one of the radii in the numerator. So inside the solenoid, we get an electric field that increases linearly with distance, where it would be equal to mu naught times the number of turns per length times the maximum current, all divided by 2, times our frequency omega, times our distance away from the center of the solenoid, times the sine of omega t. Thanks for watching.